Hello everyone and welcome to Grinds Online Ireland. I'm Tara and today we're going to be covering de Moivre's theorem and complex numbers. Now de Moivre's theorem tells us that if we have any complex number to the power, it could be to the power of 2, to the power of 3 or to the power of a million. All we have to do to find what that power is change it to polar form, so that involves finding the argument theta and the modulus or, and then putting the modulus to the power of n and multiplying the thetas by the n, where n is the power in this case. And to prove this, guys, we're going to use proof by induction. And as always, the first step in proof by induction is assume it's true for the smallest number n. So if we take in this case n is equal to 1, to show it is true, we have to prove the left-hand side is equal to the right-hand side. So the left-hand side in this case, when I plug in n is equal to 1, I'm going to get or cos of theta plus I sine of theta, and all that to the power of 1. But of course, anything to the power of 1 is itself, so that's just going to be or cos of theta plus I sine of theta. So now we know the left-hand side. If we look at the right-hand side and plug in n is equal to 1, what we're going to get is or to the power of 1 multiplied by cos of 1 multiplied by theta plus I sine of 1 multiplied by theta. And of course, anything multiplied by 1 is itself again, so we'll have or cos of theta plus I sine of theta. So the left-hand side in this case is equal to the right-hand side for n is equal to 1. So we know for n is equal to 1, it is true. Our next step now is to assume it's true for some n equal to k. So if I plug in n equal to k in this case, then I'm going to get or cos of theta plus I sine of theta, and all that to the power of k is equal to or to the power of k cos of k theta plus I sine k of theta. And this step is really important, guys, because we're going to be using this in our proof later on. So we know that this formula here is definitely true. Our next step in our proof by induction is to plug in n is equal to k plus 1. So everywhere I see an n now, I'm going to plug in k plus 1. And if we do that, we're going to get or cos of theta plus I sine of theta, all that to the power of k plus 1. And that's going to be equal to or to the power of k multiplied by cos k theta, or to the power of k plus 1, multiplied by k plus 1 theta plus I sine k plus 1 theta. And our fourth step, guys, is to prove that this is true. And how do we do that? Well, we start with the right-hand side, the or cos theta plus I sine theta to the power of k plus 1. And we have to use algebra and trigonometry to turn it into the right-hand side. Once we turn it into the right-hand side, then we know the left-hand side is equal to the right-hand side, so it must be true. So if we start off with the right-hand side, we're going to have or cos of theta plus I sine of theta, all to the power of k plus 1. And guys, you should remember from your indices rules that if ever you have an addition in the indices, you can break it up like this. So we'll have or cos of theta plus I sine of theta, all that to the power of k. So that's the first part. And then that's going to be multiplied by or cos of theta plus I sine of theta, all to the power of 1. That's from the second part. And if you're unsure in your indices rules, guys, always go to your log tables. Now we know from the previous part, guys, when we assumed n is equal to k, we know that this here must be equal to this. And if we look here in our equation, we have that formula exactly there, the left-hand side. So we can substitute in our step 2 for that, and we're going to get r to the power of k multiplied by cos k theta plus I sine k theta. And that's going to be multiplied by r cos of theta plus I sine of theta. Now looking at these two r's, we can multiply them together and get r to the power of k plus 1. And then we're just left with two brackets here in this case, cos of k theta plus I sine of k theta multiplied by cos of theta plus I sine of theta. Now we have two brackets here, so we can multiply them out. So the cos k theta plus or multiplied by the cos of theta, that's going to give us cos k theta, cos theta. We can multiply the next ones. So we'll have I multiplied by cos k theta, sine theta. And then if we do the others, we're going to get plus I sine k theta, cos of theta, and then finally we're going to have an I multiplied by an I, which is an I squared, but we know in complex numbers, I squared is equal to minus 1, so we can just go ahead and put the minus 1 there. So we'll have minus sine k theta, sine of theta. Okay, now I'm going to put all the real parts together, so that involves this part, and all the imaginary parts together, this part and this part. And if I do that in this case, I'll get r to the power of k plus 1 multiplied by cos k theta, cos of theta, minus sine k theta, sine of theta. So that's all the real parts. And all the imaginary parts then are going to be cos k theta, sine of theta, plus sine of k theta, cos of theta. And guys, if you go to your log tables on the trig page, there's loads of formulas for the trig page. And you're going to see one formula there that's going to be cos A multiplied by cos B minus sine A multiplied by sine B. And isn't that exactly what we have here in the real part, where A in this case is k theta and B in this case is just theta. So we can go ahead and substitute that in, and we're going to get cos of k theta plus theta. So our log tables tells us we can rewrite all of this as just cos k theta plus theta. Similarly, our log tables is going to give us a formula for this, where A in this case is k theta again, and B in this case is theta. And if you look at your log tables, then that's going to tell you you can rewrite that as sine k theta plus theta. Now, looking inside both these causes and sines, guys, we can factor out theta in both of them. So we're going to get r to the power of k plus 1 cos k plus 1, and then theta plus I sine k plus 1 and theta. And looking at this equation here, guys, isn't that exactly what we had to prove on this side? Which it is. So we got the left-hand side equal to the right-hand side. We started off with the left-hand side and we made it look like the right-hand side. So because we did that, then we know it's true for n is equal to k plus 1. And our fifth part then, guys, the final part of our proof by induction is stating a rolling proof is formed. So if it's true for k, and it's true for k plus 1, it must be true for any. So for example, if k was equal to 1, then it must be equal to 2. And then it must be true for 2. But then if k is equal to 2, then it must be true for 3. And you can just keep going on and on forever. So from that then, guys, from this proof by induction, you know that de Moivre's theorem is true, that any complex number to the power of n, to find that power, all you have to do is put the modulus r to the power of n and multiply the angles theta by n.